Hi, and welcome to this clip looking at an applied example of an aromatics exam question. It's had an unstructured level response section on preparation of an aromatic solid, and then it's got some more structured but applied questions on percentage yield and also deducing an equation for an unknown reaction you might not have come across before. Okay, so let's look at the level response part first. Two students aimed to prepare a sample of phenyl benzoate using the reaction below. They purified the phenyl benzoate by recrystallization from a suitable solvent. They wanted to describe and explain the steps in the purification of that organic solid by recrystallization using the properties needed of a suitable solvent. So looking a bit more closely at the first part of the question, it's about finding a suitable solvent. So they want you to think about what the properties are. Firstly, the phenyl benzoate in this case must dissolve in the solvent, ideally dissolve in the hot solvent but start to come out of solution as the solvent cools down. So for this to work, the primary intermolecular forces in work must be compatible between the solvent and the solid. If the solid undergoes hydrogen bonding, a polar solvent is the better choice, such as water or ethanol, but if the solid structure suggests mostly London forces, a non-polar solvent such as cyclohexane would be a better idea. So when you're thinking about recrystallization, look at the structure of your solid. So this time, phenyl benzoate is an ester, so there's not going to be much hydrogen bonding available, so therefore a non-polar solvent that relies on London forces is the better choice. So the first thing to write down is that you dissolve the phenyl benzoate in the minimum volume of hot solvent before filtering it under reduced pressure to obtain the impure product. That can now be redissolved and allowed to cool. And what happens next is, as the crystals of the pure phenyl benzoate come out of solution, you can refilter once more under reduced pressure and allow to dry. It's worth putting in something about why the solvent should be non-polar and relating it to the structure of the phenyl benzoate because they ask you to do so when it says including the properties needed for a suitable solvent. So let's now think about some of the things you might want to do to explain those steps. So you might want to put in the fact that the impurities and the phenyl benzoate are dissolved in step 1. And step 2 is done whilst it's still hot. And step 3 should produce relatively pure phenyl benzoate coming out of solution first, that then allows you to filter it. Now you might want to filter and also wash the solid with cold water before you leave it out to dry overnight in order to make sure that it's as pure as possible. So the next part is more structured, but it's still quite applied in places. So it says aspirin is a medicine that reduces fever and relieves pain, and some students prepare a sample of aspirin from salicylic acid. It then says before the students start the prep, they test the salicylic acid with bromine solution, and they want you to say what would the students observe. So therefore you need to think about the structure of salicylic acid, and within that structure you've got a phenol functional group. So that part is going to react with bromine without a halogen carrier. So therefore, just using bromine solution would mean that bromine decolorizes. The next part is quite applied because you might not have heard of anhydrides before. So a little bit of research would give you the structure below. And now you need to think about the salicylic acid and the aspirin. So if you look closely at the salicylic acid, you can see it's got HOOC C6H4 and then an OH group. And then the aspirin also has HOOC C6H4. Instead of an OH group, it's got OCOCH3, which equates to that part of ethanoic anhydride. So therefore, that must mean that bit splits off, the ethanoic anhydride, to become part of the aspirin. So what's left behind, in both cases, comes together. So therefore, the OH from the salicylic acid must have been removed, and the remaining part of the ethanoic anhydride must combine with that to make CH3COOH, which is what they want you to put in that blank space there. The next part of the question asks you to think about some data. So it says the density of ethanoic anhydride is 1.1 grams per centimeter cubed. So therefore, density is mass over volume. So mass will be density times volume. So in this case, it's 1.1 times 10, which gives you 11 grams. So taking the molar mass of ethanoic anhydride is 102 grams per mole. You divide the mass by the molar mass to get 0.108 moles. And then you need to work out the moles of salicylic acid. So again, you work out the molar mass of salicylic acid is 138 grams per mole. divide 6 grams of salicylic acid from the question by 138 to give you 0.0435 moles. Now that number is less than 0.108, so therefore the ethanoic anhydride is in excess. So the final part of the question, it says the students pour their hot solution into water and aspirin crystallizes out as the water cools. So that tells you, first of all, that aspirin is a solid, and then it means you need to think about the suitable properties of a solvent for recrystallization. So if the aspirin crystallizes out, that means as the water cools it's not soluble, but if it's still in solution when it's hot, it means it dissolves in hot solvent, but when the solvent is cold, the aspirin is insoluble. Now, because aspirin is a solid, the way you test for the purity of a solid is to measure its melting point and then check that melting point against known data for that particular solid. So, how do we get the percentage yield that's at the bottom? So let's think about the logic behind that. First thing is the salicylic acid and the aspirin are equimolar. So therefore the expected number of moles of aspirin is 0.0435. So the actual number of moles of aspirin is 3.1 grams over 180. So 180 being the molar mass of the aspirin. So that gives you 0.0172. So you divide the actual moles by the expected moles and multiply by 100 to convert it into a percentage. And that's where we get 39.5 from. Okay, so hopefully this has been a fairly useful clip looking at how you can go through a range of different types of questions that are more applied, including percentage yield, including deducing an unknown equation, and also thinking about some of the steps in the techniques we use to make and purify organic solids. So until next time, thanks for listening and see you soon.